Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Ambesh Singh, Roberta Humphreys, and Lucy Ziurys with us today. Hello, Ambesh, Lucy, and Roberta.
Hi, Frank.
Cool.
Hi.
Been a while since I did a trio, so this will be fun. And Ambesh, let's start with you. Where are you located at?
I'm in Tucson, University of Arizona. I'm in grad school, about to graduate soon.
Oh, so I get to say Dr. Ambesh very soon.
Yes.
Soon, yes, soon, very soon.
Congratulations. That's
Thanks.
awesome. Very good. And Roberta, where are you located at?
Twin Cities, Minnesota.
Very
That's
good.
Minneapolis, St. Paul, University of Minnesota.
Very nice. And are the trees turning colors yet in Minnesota?
Well, yesterday it was 91 degrees here.
Oh, you were hotter than Phoenix, just about.
Hotter than Tucson.
Yeah,
Amazing.
91 degrees, and we haven't even had Indian summer yet.
Oh, wow.
It was too early for Indian summer. Yes, trees are trying to turn. They're slowly doing it. Yeah, They're falling off the trees. The leaves are, yeah. Starting to look like fall, except for the temperature. We're going to eat outside on the deck tonight.
Nice. Very nice. Very nice. Lucy's already outside on the deck down in Tucson, so, you know,
Yeah,
all good.
it's about 85 degrees right now here. Very nice from what it's
Yeah,
been.
it's very lovely.
Yeah.
We have been waiting for this heat break for a while. So.
Yes.
So, very cool.
This is it to us, I think.
Okay, very cool. And Ambesh, what do you like to do for research?
So I do rotational spectroscopy in lab, and I also do observational astronomy. So I look for molecules, especially that we study in our lab, mostly metal-containing small molecules, and make inferences about the sources where we observe them.
And Lucy, what do you like to do for research?
Oh, I like to study astrochemistry in a big way. So I study the composition of many different types of objects, you know, molecular clouds, circumstellar envelopes of evolved stars, planetary nebula, and now we've gotten into the chemistry of these hypergiant stars. So it's all very exciting. And I also do laboratory spectroscopy and laboratory astrophysics as well. So a big combination of things.
Awesome. And Roberta, what do you like to do for research?
Well, I kind of always describe myself as a bit of an old-fashioned observational astronomer.
Okay.
I do stellar spectroscopy. I classify stars and other galaxies, but my favorites are the biggest, the brightest, the best ones, the most massive stars. And we're going to talk about my favorite star today.
Oh, your favorite one. Very cool. Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It is open access era, people. You can go grab a copy for free. Go get one. ALMA reveals hidden morphologies in the molecular envelope of VY Canis Majoris. And Ambesh, Roberta, and Lucy, take us away.
Well, I'll tell you, this was an interesting project because it began with a collaboration with Roberta on VY Canis Majoris. I was interested in it from the chemistry aspect and other aspects, and Roberta was very interested in understanding how these stars evolve. And, you know, we decided we needed to write an ALMA proposal. And the funny thing about VY Canis Majoris, it's a small source on the sky. But in past research and some single dish observations that I had been doing, we realized that, you know, the envelope seemed to be bigger than what we saw in the Hubble Space Telescope image.
Okay.
And this led us to write an ALMA proposal, but with spatial resolution that would enable us to look at possible larger scale structures. And you'll see where that led to. Now, VY Canis Majoris is a very interesting object, and Roberta can fill us in on that.
Well, okay. Well, I think it's best known, well, first of all, very high mass loss rate that we knew even many years before we took the first Hubble images. Very powerful infrared source. It was known as an OHIR source and was already known as one of the most luminous red supergiants and one of the biggest stars that we knew of. So actually, we could turn to figure 4 right now and show people the famous Hubble picture, the famous multicolor picture.
This is going to be the money shot, people. Figure four, and here we go. I'm going to blow this up a little bit so people can appreciate all the resolution that went into getting this.
Yeah.
There we go.
Well, there on the right is the famous multicolor Hubble image. And actually, I have to admit that when we first got that picture, I just went, oh my gosh, because there was the star's mass loss history just staring right at you. You couldn't miss it with the multiple arcs and several clumps of small knots, and you would zoom in on it on your computer monitor and just be amazed, because even a picture there, you don't see the detail that's really there. Just it was just little knots and arcs all over the place. And so it wasn't long before we were able, with subsequent images and spectroscopy, to begin to recreate its mass loss history. And basically, we can trace these ejections back about 600 to 800 years ago. So the star's been blowing the stuff out for a long time, and even quite recently in the last century, early 20th century, there were several outflows.
Cool.
Yeah, so what we're looking here is the envelope, and the star's that little cross in the center. And I think this figure kind of shows what we found. We imaged the envelope in carbon monoxide, which is the map you see here. Carbon monoxide, J = 2:1 transition at 230 gigahertz or thereabouts. And on the right, the HST image is what we thought the envelope looked like. And on the left is its real, it's the complete image. Okay, and you can see there's all these new structures off to the northeast and the east that didn't appear in the HST image. And this, has a lot of impact for, we've missed major mass loss events, and ALMA and CO emission has brought them in. And the other interesting thing is that you see these various arcs and knots that Roberta has been talking about in the dust. This is starlight reflected off dust. And then you see the same features in carbon monoxide, meaning that the gas and the dust are very well mixed. Anyway.
Very cool. One question. We have is the same spatial scale here on the Hubble image as it is on?
Yes, identically.
Okay, good. Thank you.
So the features marked A, B, C, D, et cetera, are actual features that Roberta identified, or at least some of them that Roberta identified a couple of years ago, associated with specific mass loss events. The A is arc 1, B is arc 2, E is the northwest arc, et cetera. And they're there in CO almost identically.
That must tell us something.
Yes.
Indeed.
Now, we were the first ones to really image VYCMA with ALMA with this kind of extended spatial resolution. And maybe Ambesh could talk a little bit about the reduction he had to do to get there.
Yeah, I don't think this was a straight pipeline.
No, this was not.
Right, so let's hear a little bit about that data reduction.
So the most challenging part of the data reduction was definitely trying to get all this really heavy set of data reduced and clean, so we can see all these fine large-scale structures that was missing in the uncleaned image. So we really had to.
Yeah. How many resolutions did you end up combining to get those maps?
So I combined 3 different resolutions: 250 milliarc-second resolutions from ALMA, 1 milliarc-second resolution from ALMA, 1 arc-second resolution from ALMA, and 30 arc-second resolution from SMT. So once we combined all of those resolutions, that's when we get the kind of image we see in figure 1 and figure 2. So if we look at figure 1, we have 2 different images of the COJ = 2:1 line. The figure to the left is a slightly a higher resolution of the 250 milliarc-second, and figure to the right has the combined SMT the
Got it.
single disk data from the Arizona, as well as the two ALMA resolution that we observed them in, which is 1 arc second and 250 milliarc second.
Yeah, and let me explain what SMT is. SMT is a sub-millimeter telescope run by the University of Arizona. It's a 10-meter dish, and so its resolution on the sky, as Ambesh mentioned, was 30 arc seconds. And this gave us the so-called zero spacing, and by combining these maps together, we recovered all the flux. So we believe these are the most complete maps you'll ever see of the envelope of VYCMA.
Until you do it again.
Right.
Very good.
One unorthodox things that we did for this data is that we looked at moment 8 images. Moment 1, usually people look at moment 1 images,
Okay.
but they are not
zero.
Yeah, moment 0 images, which are not which do not show some of the structures that we can clearly see with moment 8, which shows the maximum intensity for each features. So
Okay.
that really helped us pinpoint some of these structures to the left, to the southeast, which were missing in the pipeline data. So the cleaning really revealed some of the features that would have been easily missed if we hadn't done the cleaning properly.
Beautiful.
And
Beautiful.
not only did we model image CO, but we also image HCN. So we could go on to figure 2 and have a look at that. Now you can see that HCN isn't quite as dramatic in its tracing the envelope as CO, but that's because HCN in the J = 3 to 2 line at 265 gigahertz, it's tracing the higher density material. But
Okay.
even very faintly, you can see this image, this arc off to the northeast, a little bit in HCN. It's probably showing tips of shocks, of shock waves.
Fair enough.
So yeah, but
And then and then again on the right, it's combining the
yeah,
yeah,
3 different resolutions.
yeah.
We were absolutely, when we saw the CO map, we were absolutely surprised. We expected a somewhat more extended envelope, I think, than the Hubble Space Telescope image. But when we saw this was like, wow, you know, we never expected so many new outflows at such a large spatial extent. It was really quite amazing.
Very nice. Very nice. Yeah, it's just a sort of a random question. I don't mean to put anybody on the spot, but do you get a sense of what the velocity of those outflows are, and by extension,
yes,
how old some of those mass outflows are?
Well, if we go to figure 3.
Okay. Leading question. There we go.
We can make spectra
Okay.
in the different molecules in those different regions with ALMA data reduction. And you can see, you know, some of the new features, what we labeled the northeast extension, the northeast arc. You can see that on the right there. And because those are the line profiles from those particular regions.
Okay.
And this, you can see it's in velocity space, LSR velocity. So we do have velocity information from these different outflows, whether they're blue shifted, they're red shifted. And if you really do things properly, and Roberta can tell you about that, you can get, you know, more than velocities out of the spectra. You can actually get the projection of where the clump is flowing more accurately.
Okay.
But you know, you can see that the northeast extension is blue shifted, and the northwest arc is primarily red shifted. So you've got all these outflows going in different directions. It's very interesting, a very complex envelope, and I think more complex than we thought.
Indeed.
I hope that answers your question.
Yes, it does. Roberta, you want to add anything on that?
So one of the things we did do with Hubble was we got second epic images several years after the first beautiful pictures. We went back and got them again, and it allowed us to measure proper motions for some of these would be the optical features, the ones you see in the HST images. So in addition to the radio or Doppler velocity, we also had the transverse velocity, velocity across the line of sight. So you get the total motion, and you could also get the projection angle. in addition to its total velocity, you knew its distance from the star, and you got the angle that it was projected at. So you could reconstruct basically these outflows when they were kicked out of the star, what directions they were moving, and put together quite an interesting history.
Very cool.
And this is what we're hoping to do with this data in more detail as we go along.
Very cool. I'm just going to sit on this because I like this image so much. I think it's just lovely. Very cool. Very cool.
Now, and Roberta can comment more on this. No one seems to really completely understand the evolution of these very, very massive stars like VY Canis Majoris. There are not that many of them in the first place. I mean, I think the mass is estimated to be about 40 solar masses. And Roberta can tell you more since she's the real expert on this, but some of they used to think that these sort of massive stars all died by going supernova, right?
Sure.
And now it's thought that some of them just quietly collapse into black holes. Therefore, all this material that's being thrown out in the envelope just slowly, or maybe not so slowly, flows into the interstellar medium and contributes to the material that forms diffuse clouds. And a lot of that material is full of molecules and dust. So, you know, it has an interesting implication for understanding how diffuse clouds form and so forth. But Roberta can comment on the, you know, some of the, you know, the more details of our lack of knowledge of what happens to these stars. And this is why images like this are so important, because, you know, as far as stellar structure and evolution is concerned, a lot of our models, maybe shouldn't say that, just don't seem to work. You know, we don't seem to understand mixing in stars and convection. And so we need observations to give our theorists, you know, more benchmarks by which to postulate what happens to these very massive objects. But Roberta can say more.
Okay, I'm getting the hint here. Okay, well, I think you might recall, Frank, when Stephen Smart came out with this conclusion now well over a decade ago, I think, that the progenitors of the type 2 supernovae, which we all thought were red supergiants, right? Stars below a certain mass, say 25, 30 solar mass, were all going to go through the red supergiant stage. Yes, we know that. And then they were also supposed to behave themselves and explode nicely as type 2 supernovae. But then he found, well, wait a minute, there's a problem with the masses of the progenitors. And he concluded it was somewhere around 18 or 20 solar masses. So the question then was, and by the way, that result has been confirmed by some other studies. So it's pretty, really. So what happened to those all those red supergiants up above 18 solar masses? There were certainly a lot of them sitting there in the HR diagram. One possibility, just simply collapse to a black hole. Another possibility is that they evolve back to warmer temperatures. They go the other way on the HR diagram, back to hotter stars, where they would then nicely go supernovae, presumably. So those are kind of the two options, and both of these options depend on the mass loss from the star.
Yes, it does.
And particularly whether or not it's going to evolve back across the HR diagram to warmer temperatures. And so here we have VY Canis Majoris, and there's a few others that Lucy's also worked on, like NML Cygni, and I've worked on like IRC plus 10420, that are pumping the stuff out. So they're good candidates for that post-red supergiant evolution. So, but you know, I was hoping maybe to live long enough to see some of my favorite stars, you know, go supernovae. But apparently VY Canis Majoris probably won't do that. I think it won't do it anyway.
Rats.
So, you know, you see this very irregular, you know, if you look at an asymptotic giant branch star, usually you see a nice spherical envelope. Here we see anything but spherical. And this sort of mass loss, it's irregular, it's directional, and there's a big question of how is it caused? Right?
Stuff is going out like this, it's just tossing this stuff out in all sorts of directions, right? How's it doing that? Well, we have a local example. It's called the sun.
Fair enough. Fair enough.
Not as
Okay.
dramatic.
Not as dramatic, but fair enough.
Not as dramatic, but it certainly provides us with some clues. And we
Yeah.
know that we see
Yeah.
star spots on a variety of cool evolved stars. We see their surfaces. Betelgeuse being one of them that recently did something active. So I think we're looking at is the surface activity. Surface activity, large-scale convective cells, and very likely the missing piece of the mystery of the story still is magnetic fields.
Okay. Okay.
What's the role of the magnetic fields? There's a lot of circumstantial evidence.
Yeah.
And again, from the Maser observations, that there's magnetic fields out in the extended ejecta of VY Canis Majoris.
Okay. Cool.
Yeah, so that's probably the answer, but you know, people like to debate it.
Absolutely. Absolutely. And I do wish you a supernova.
Yeah,
A core collapse event.
yeah, core collapse, right.
Very, very cool. And I just want to mention there are a couple of awesome appendices, and one I want to come to a little bit just to mention, because it's going to lean toward the future a little bit here, is table B1. What are all this?
When we did our imaging, we imaged many different molecules over a certain spectral region. And, you know, years ago, with the submillimeter telescope on Mount Graham, we had done a spectral line survey of VY Canis Majoris. So we measured all the spectral lines between 215 and 285 gigahertz in the 1 millimeter region. Okay. And so we selected regions of that survey to image with ALMA and got all these very interesting molecules, which we're currently making images of, including the phosphorus containing species PO and PN.
Nice.
There's sodium chloride in there,
nice.
And
SiO,
etc. And you know, we were almost done imaging the PO and PN maps, and they're saying something perhaps about where phosphorus comes from in nucleosynthesis.
How interesting.
Yeah, and this will be coming out sometime. And
Wow.
So you're learning not only, you know, and also about the chemistry, how phosphorus monoxide may be formed, but there's a lot of phosphorus containing the abundances of both PN and PO are quite large in VY Canis Majoris. And it makes one wonder whether in surface activity and the dredge up that occurs, that we're not dipping into the carbon burning shell and pulling out some extra phosphorus. And maybe this is why we see these phosphorus molecules so chemically enriched, but that's a topic of a different paper. It's just, you know, we've got a lot more data and a lot more interesting things, I think, to discover from this unique data set that, you know, ALMA has helped us obtain.
Awesome. Very cool. Very cool. And this is just the teaser letter. So Ambesh, Roberta, and Lucy, I want to thank you so much for walking us through this very awesome discovery of a little bit of VY Canis Majoris.
Beautiful star.
Beautiful star. So we mentioned a little bit there at the end, B1, and I'm looking forward to seeing these new data sets come out. But are there other things that could be done? Is there some laboratory astrophysics that could be done? Is there some additional observations at different wavelengths that might be useful? Is there some theoretical work that could be done? So just sort of where do you think we go with this on this star over the next 2 to 5 years before it goes supernova for Roberta?
I think one can say all of the above. You know, some of the lines we see in VY Canis Majoris are unidentified.
Oh.
And so that means, you know, one has to go into the laboratory and pick some possible species and measure their spectra. So yes, laboratory astrophysics will definitely, you know, be involved in the future. Wow. In terms of theoretical modeling, someone's got to understand how this outflow, you know, this mass loss occurs in this star, and Roberta can comment on that more. But there's a lot of theoretical work, I think, that needs to be done. Roberta?
Well, that's what, as I said, that's where the big mystery is. But actually, some very good ground-based data is being obtained with the ESO telescopes, the VLT. They have these
VLT.
very, high-resolution spectrographs. They work in the optical and the near-infrared, and they're really getting some interesting, nice observations, very close to the surface. Well, you shouldn't say surface of the star. It's not really have much of a surface. But anyway, getting quite close to the star and seeing a lot of structure in different emission lines and so on. So I think that there's going to be learning more about the material really close to the star. It would be great if VY Canis Majoris would go through another one of its brightly or fading episodes. In the first half of the 20th century, there were 7 episodes when the star faded by 1 or 2 magnitudes, lasting about 2 to 3 years each. Now, you remember what Betelgeuse did?
Yeah.
Yes.
The great dimming of Betelgeuse?
Yes. Mm-hmm.
Well, VY Canis Majoris was doing the same thing. It was having outflows that were forming dust and obscuring the star. And then it would recover back to its former brightness and do it again. Well, what I'd really like to see is the CVY go into that kind of an active period now, when we're watching it carefully and we can really zoom in on it and get good spectra and photometry. It'd be exciting.
Indeed.
Get a close up.
Indeed. Very cool. Very cool.
Ambesh, if you were to do some more observations, what would you do?
There you go.
I would really focus a lot more on metal containing molecules in UICMA, maybe increase the resolution even more, see it even closely, because a lot of metal containing molecules has been detected in UICMA in past that are titanium containing, vanadium containing. So those things are very interesting. And plus, in our Tenabomb survey, like Dr. Ziurys mentioned, there are so many unknown lines and that are left to be discovered. So we need to do a lot of work in lab and to detect some of these metal containing molecules in lab before we can observe them in hypergiant star and try to understand what this means for what seeing all these heavy metal containing molecules means for sources like this, because we don't see it as often in other kind of sources like molecular clouds and AGB star. So the fact that we see titanium, vanadium containing molecules in VICMA must mean something special about this source.
Yeah, and we didn't really go through this part of the paper, but we've been looking at carbon-12 to carbon-13 ratios in the different outflows.
Yeah.
And, this is a star you might think has very low carbon-12 to carbon-13 ratios because it's a supergiant. It's a giant star. There's a lot of dredge up of carbon-13 from the hydrogen burning shell. And yet we find a ratio, this is preliminary, that's sort of in between what you see in a lot of red giants and what you see in AGB stars. Okay. So, the potential there to really look at, some of the details of nucleosynthesis through isotopes, through production of unusual elements, it's all there. Just, there's a lot of work that needs to be done and a lot that can be learned.
I think it was one of your colleagues that said it's isotopes that keeps theorists honest.
Yes.
Go Dave, there you go. Very cool. All righty, Ambesh, Roberta, and Lucy, thank you so much for talking about your article. And that will do, everyone. And I hope this made your astronomy day way better. And we will see you on the next one. Bye-bye.